So, good morning everyone. I am Ramaseshan. I am a PhD student at IIT Madras under Professor Arun Mahindrakar. So, I will be giving a tutorial lecture on bifurcations. So, I will be solving some 3 problems relating to bifurcation analysis. I have uploaded the problems in the NPTEL portal. So, there are about 10 problems for your practice along with the solutions. So, I will be explaining 3 of them in here now. The rest of them you can see the material uploaded, and then if you have any doubts as usual you can ask in the forum. So, we will begin now. So, the first question is what is called as famously the harvesting problem. So, I will first describe the problem. So, here as usual it is a one dimensional dynamical system. So, here y of t belonging to R is the dynamical variable. It is nothing but population, let us say, of a fish in a river or a sea, and the dynamics of the population of the fish is given by this equation dy by dt is equal to y into 4 minus y minus k. So, let us first analyze why this model makes sense for the scenario that is presented. So, if we expand this, we will get 4y minus y square minus k. Now, this 4y arises because of the growth or reproduction of the fish. So, more the fish, more they reproduce, right. So, higher the fish, bigger is the growth rate. So, to capture that proportionality, we are introducing this term 4y. So, this 4y captures the growth or reproduction of the fish, but it cannot grow forever, right. As the fish population increases, we cannot keep on growing to infinity, right. There should be another term that reflects competition or space constraint or some other food competition when the population is very high. So, we have another decay term which is minus y square that captures the competition or deaths due to competition or space constraint. And why it is minus y square is because if you see the function y square, it grows much slower than y in the beginning, and after some time only it takes over. So, if you see y square function and contrast it to the linear function y, initially it is much slow. The initial effect of y square is very negligible. So, at lower populations we expect the competition to be a negligible effect. So, when the population density is very low, there will typically be enough space and enough resources for everybody, right. That is why we have a minus y square here. It is only when the population gets really high we get to have problems, and when the population gets really high, competition is a more severe issue than growth rate. So, that is why we want a function which for lower values of y is much smaller, but takes over very largely at higher values of y, and this function y square takes it. And we add a minus y square here because we want the decay rate. So, since this captures the death, should be a negative. So, initially the death rate due to competition is really low, whereas at a higher population the death rate is really high. So, this term is a competition term, and this term k is called the harvesting rate or a fishing rate. So, this what does it reflect is, let us say somebody is fishing the river or sea where the fishes are living. So, they keep on depleting the fish at a constant rate k. So, this is the dynamical system that is given to us, and the problem that is asked is what is the critical fishing or harvesting rate above which the population of fish becomes extinct at steady state. So, intuitively we realize that when the harvesting rate is really high, the fish population should get extinct, right. So, we have to do that mathematically, we have to prove this mathematically. So, this is a bifurcation study because here if you see it is a dynamical system and k is the parameter. So, k is the bifurcation parameter here. So, as k increases we want to know what happens. So, we want to study the equilibrium points, how they behave. So, let us do the bifurcation study now. So, first let us analyze this problem graphically. So, we once again have dy by dt is equal to y into 4 minus y minus k. Now, the question is what are the equilibria? Where are the equilibria? For equilibria, we know that dy by dt is equal to 0 at equilibrium. So, this implies y into 4 minus y, which is nothing but 4y minus y square, should be equal to k. So, this is the condition for the equilibrium. So, the equilibrium points are nothing but the solution to this equation. Now, this is a simple quadratic equation. We know how to sketch quadratic equations and their solutions. So, here we have. So, here is the y and here is this function. So, this function let me call it g of y. G of y is equal to 4y minus y square. Now, how does this function look like graphically? So, when y is really small initially, this looks like the linear function 4y. So, when y is really small, what we have is, it looks like this. So, this line looks like 4y. Now, as y becomes really large, it begins to look like minus y square graph, because minus y square dominates 4y when y is really large. How does the minus y square graph look like at, it looks like an inverted parabola, right, something like this. So, what happens is, it has to do something in between. So, this is the graph and we are not bothered about y negative, because physically population cannot be negative physically. So, we are not bothering about what happens when y is negative, but if you want for your reference, it will keep going like this, because minus y square it keeps going like this. So, the linear and quadratic part kind of reinforce each other. So, this is the graph of the function 4y minus y square, correct. Now, for equilibrium, so let me erase this unwanted things. So, this is the graph of the function 4y minus y square. So, for your reference, I am writing the function name. Now, for equilibrium, this has to intersect k. So, this is the line y equal to, so this is the line, let us say k. So, this is the place, let us say, where f of f is equal to k. So, this is the value k. Now, for equilibrium, these two curves have to intersect, because these two equations have to hold simultaneously. So, this k should be equal to 4y minus y square. So, typically we say we get two equilibrium points. But do we always get two equilibrium? No. As k increases, this line shifts upward. We see that the equilibria get closer and closer. And after some critical value, k critical, so let me call this value corresponding to the vertex of this parabola, k critical, we see the two equilibria merge into a single degenerate equilibrium, and beyond k critical there are no equilibria at all, they just vanish. So, this is related to the critical harvesting rate that was asked in the question. So, let us come back. So, let us analyze the flow of this dynamical system. I will draw the vector field, it is a line, it is very simple. So, let us take the value first k equal to 0, there is no harvesting at all, we are nobody is fishing in the rivers, all the fish are very happy and happily swimming around. So, now we see that there are two steady states, one is 0 which is one equilibrium. So, this is 0 and there is another equilibrium which I call it, let us say k. So, we see that when the harvesting rate is 0, there is one equilibrium point at y equal to 0. So, and another equilibrium point which I have called it k. That k can be found by solving the quadratic equation 4y minus y square equal to 0, which here is nothing but, so if you solve this quadratic equation, it is y times 4 minus y is 0. So, the k is equal to 4 here. And now, if you look at the this quadratic function, between y is equal to 0 and y is equal to 4, dy by dt is positive. So, dy by dt is positive in this region. Now, when dy by dt is positive means y increases with time, right, that is what the derivative says. So, if you look at the flow of the vector field, it will be like this. So, the population evolves like this. Whereas, when y is beyond 4, dy by dt is negative, because dy by dt is this quadratic and this quadratic is negative, which means y decreases. So, now you see there are two equilibria, one corresponds to 0 and we know the population is 0 means there are no fish, another equal to 4. So, we see that when the harvesting rate is 0, even when you have a slightly non-zero amount of fish, they will reproduce and grow and grow. They will keep on growing until they reach y equal to 4. So, the population will settle at y equal to 4, and if suppose it gets greater than 4, the competition and all the space constraint, they will lead to deaths and the population will level down back to 4. So, this 4 is kind of called carrying capacity of the river in population biology literature. So, we see that the carrying capacity is 4 when the harvesting rate is 0. So, the population settles at 4. Of course, the physical population of 4 may not make sense, you may treat y as population in thousands or 10,000s to make more sense out of it. Now, what happens when k is slowly increased from 0? So, when k is slowly increased from 0, what happens is the 0 steady state, it shifts somewhere over here. So, let me go to the next page. So, when as k increases, so this is when k equal to 0 we saw, there are two steady states 0 and 4, and this is unstable and this is stable. So, the population kind of settles around 4. Now, as y increases, as k increases, what happens is this 0 steady state, if you see, so this 0 steady state, it kinds of comes here, it kinds of comes closer, because now it is not the intersection of the parabola with 0, but it is the intersection of the parabola with k. So, this comes here and this comes, so the left steady state moves a bit to the right and the right steady state moves a bit to the left. So, what happens here is these two equilibria, they kind of come here, but the stability is maintained if you go by the logic. Dy by dt is positive in the region in between and it is negative, this is negative. So, this is negative. So, now we see a very, so the population now let us say is 3.5 and this is let us say 0.5, just for some simplicity, this may not correspond to actual values. Now, we see a very drastic behavior now. When the population is above 0.5, it settles to 3.5. It didn't settle at 4, it settles at a slightly bit of lower value because it is expected, right? When you start fishing, the steady state has to be lower. But earlier, any non-zero population of the fish tends towards 4, whereas now here if you see, the initial population of the fish has to be beyond some threshold, which is 0.5. If it starts anywhere below 0.5, it will decrease. Of course, it can't go to negative values, it will settle at 0. So this negative thing is not feasible. The population cannot keep on going to minus infinity. This reflects that our model is not that good. So of course, I didn't expect an accurate model because I just want to explain the overall view. I don't want to give an accurate model. So we see that now as k increases further, these two equilibria, they get even more closer, which becomes worse. So they kind of become very close now. So this is again 0 and this is 4. So they kind of, sorry. So now what we see is they kind of come really close. So only in this narrow band you have a non-zero steady state. Anywhere the population starts below this value, it will decrease and the fish population becomes extinct. But if you are luckily enough to start in this narrow band, it will go and reach another steady state. Now when k exceeds the critical population level, so when k exceeds the critical value, suddenly there are no equilibria, and you observe that dy by dt is always negative because dy by dt is 4y minus y square, this quadratic minus k, and when k is really high, it will beat this term. So dy by dt will always be negative now. If you see, this always beats this. So this straight line always beats this curve. So this beats this. So the dy by dt will always be negative. So what happens tragically? Tragically, when k increases beyond the critical value, the population just decreases. All the fish becomes extinct. So how do you calculate the critical level of harvesting? Again, it's very simple algebra. We have to find this vertex of this parabola. At the vertex point, the derivative vanishes. So if you see the derivative of this, because for a local maximum, derivative vanishes. If you take the derivative, what's the derivative of this? 4 minus 2y is equal to 0, because we want the derivative to vanish. So this gives us 2y equal to 4, y equal to 1 by 2. Substituting y equal to 1 by 2 here, it gives the value 4 by 2 minus 1 by 2 square. So this 4 by 2, which is 2, minus 1 by 4. So 2 minus 1 by 4, whatever value this fraction is, that is the critical harvesting rate. Beyond this harvesting rate, you are doomed. The population of the fish in the lake or the river or the ocean will go extinct. So this is a typical bifurcation example. If you plot the behavior, so if you have k, so if you plot the equilibrium, y equilibrium versus k, we see that at k equal to 0, we have one steady state at 0 and another steady state at 4. As k decreases, what happens is, so this was unstable, so I denoted by a dot, and this was stable, so I denoted by the dash. So this, they come closer and closer to each other, and beyond this critical harvesting rate, so maybe, yeah, so they kind of merge here. After this, there are no equilibria at all, they just vanish, no equilibria. So what kind of bifurcation this reminds you of? So this blue color corresponds to stable equilibrium, whereas the yellow color corresponds to unstable. So what does this remind you of? If you look at it in the backward direction, till a critical value there are no equilibria, and suddenly there are two new equilibria coming out of the blue. So this is nothing but a saddle node bifurcation. So this So, when you do not have any equilibrium and suddenly two new equilibrium are born where one is stable and another is unstable, that is the signature of a saddle node bifurcation. So, the reason for existence of a critical harvesting rate is because of this saddle node bifurcation. So, with this we can see how simple models can capture the behavior of the system. So, now you move on to problem number 2. So, there we are asked to analyze the behavior of the dynamical system dx by dt, where x is in R, dx by dt mu x plus x cube minus x power 5. So, this is the system. Now, what does this remind you of? When we have only mu x plus x cube, this was nothing but the normal form for a pitchfork bifurcation. So, the normal form for a pitchfork bifurcation was dx by dt is mu x plus x cube, right, or minus x cube, does not matter. So, now we add a perturbation to this pitchfork. We have an x power 5 perturbation to the pitchfork. We are now asked to analyze what is the behavior of this system. So, I will again write the system dx by dt is equal to mu x plus x cube minus x power 5. Again we have to find the equilibria. So, the equilibria at equilibria dx by dt is 0, and hence if you take x common we have mu plus x square minus x power 4 is equal to 0. Now, definitely x equal to 0 is always an equilibrium for any value of mu. So, we are guaranteed the existence of one equilibrium for sure. So, the other 4 candidates, so because it is a 4th order polynomial, at most it can have 4 solutions. So, when you are lucky enough you will have 4 solutions. When we are not lucky we may not have any solution. So, the number of equilibria can be either just 1, which is this alone, or it can be 1 plus 2, which is 3, or you may have 1 plus 4, which is 5. So, the number of equilibrium points can range anywhere between 1, 3 and 5. So, let us analyze the roots of this equation mu plus x square minus x power 4. It is same as the roots of the equation x power 4 minus x square minus mu equal to 0, right, because if something is equal to 0, its negative also better be 0. Now, we can write this as x square whole square minus x square power 1 minus mu equal to 0. Now, this is a quadratic in x square. So, by the quadratic formula, the roots will be x square is 1 plus or minus root of 1 plus 4 mu by 2. Now, as usual, the discriminant of this quadratic plays a very important role determining the number of solutions, right. When the discriminant is positive, 1 plus 4 mu is positive, x square will have 2 solutions, and when 1 plus 4 mu is negative, x square will have no solutions. So, now let us now analyze the case 1, when mu is less than minus 1 by 4, which is same as saying 1 plus 4 mu is less than 0, because if we rearrange we will get mu less than minus 1 by 4. Now, when mu less than minus 1 by 4, no solution for this quadratic. So, this implies x equal to 0 is the only equilibrium point, and we want to know whether it is stable or not. So, for stability we want to know what happens when x is perturbed slightly from 0. When x is really small, we can neglect x cube, x power 5 and so on, and hence we get dx by dt is equal to mu x, and mu here is negative because mu is less than minus 1 by 4, which implies mu is negative. Now, when mu is negative, the linear equation dx by dt equal to mu x is stable, right, because it's the only solutions for this differential equation are x of t is equal to x of 0 e power mu t, right, and when mu is negative everything decays to 0. So, in that case what happens is, so in case 1 when mu is negative, we have only one equilibrium which is 0 and that is stable. So, we will have the portrait like this, correct. So, this is the case when mu is when mu is less than minus 1 by 4. So, when mu is less than minus 1 by 4, only one equilibrium, and since mu is negative, this will be stable. So, this origin is stable. So, I will write S for stable and US for unstable. Now, we will come to the next case when mu is bigger than minus 1 by 4, but is still negative. So, in that case what happens is, origin is always an equilibrium, no doubt at all, indeed, and it will still be stable because mu is still negative. By the same argument, origin will be stable. But what happens is, we witness the birth of two other equilibria, because this quadratic, if you see x square, what was the quadratic? X square is 1 plus or minus root of 1 plus 4 mu by 2. So, this has two roots, and if you see, if you look very carefully, when 1 plus 4 mu is bigger than, so when this is bigger than 0, but it is less than 1. So, when mu is bigger than minus 1 by 4 and less than 0, 1 plus 4 mu is essentially greater than 0, but less than 1. So, if it is less than 1, we have both the roots. If you compare both the roots, one root is positive, one root plus, that is positive, because 1 plus root 1 plus 4 mu by 2 is positive, because mu is positive and every other thing is positive. And if you see the other root, so this is root 1, and if you look at root 2, which is 1 minus root of, so when mu is kind of positive, you will have a root indeed, but when mu is kind of very small, does not dominate, what happens to this? What happens to this root? This root is also positive, right, because when this is less than 1, so let us call this quantity alpha. If alpha is less than 1, we will have 1 minus alpha is positive. So, this 1 minus alpha by 2 will also be positive. So, this will also be positive. So, we have two positive roots for x square, which means we have 4 roots for x, because if x square can take two positive values alpha and beta, then x can take either plus or minus root alpha and plus or minus root beta. So, we have now 4. We have 4, the maximum possible roots for this fourth order equation, x power 4 minus x square minus mu equal to 0. So, we now have the maximum number of roots, and now what happens is, so we can both of these, so these are the positive roots, these are plus root alpha and this is plus root beta, and this is minus root alpha and this is minus root beta. We have now two other roots. So, again this typically, if you see, from nowhere we suddenly get two equilibrium. So, we suddenly get two equilibrium from nowhere. So, again it is a signature of a saddle node bifurcation. So, we didn't have any equilibrium, and suddenly we now getting two equilibrium. So, this is signature of a saddle node. So, if you look at the stability by the continuity of the vector field, if this points left, this has to point right and this has to point. So, if this points right, this has to point left, and if this points left, this has to point right. So, we see that there are 4 equilibria now alternating in stability. So, this is the scenario when, in case 2, when mu is bigger than minus 1 by 4, but still is negative. Now, what happens in the case, next case when mu is positive? So, now we will look at case 3. Mu positive, again we have x square is 1 plus or minus root of 1 plus 4 mu by 2. When mu is positive, 1 root 1 plus root of 1 plus 4 mu by 2, this is positive, no doubt about it. So, we will get 2 roots. So, let us say we call this alpha, which is positive, we will get 2 roots, x is plus or minus root alpha, we will get 2 roots for x. But when mu is positive, 1 plus 4 mu is bigger than 1. So, the other root 1 minus root of 1 plus 4 mu by 2, this becomes negative because this becomes bigger than 1. Square root of a number bigger than 1 is still bigger than 1. 1 minus a number bigger than 1 is negative. So, x square equal to some negative number, does not make sense. So, we have no solution for this. So, this has only 2 roots now. So, apart from 0, you will only have plus root alpha and minus root alpha. And if you do linear stability analysis, dx by dt is mu x. When mu is positive, it is unstable. So, origin flips stability, it changes from stable to unstable when mu changes from negative to positive. So, we will just have something like this, and hence if we plot a diagram of how the equilibria vary with the parameter, what we will have is, so this is mu and these are the equilibrium values. So, origin is always one equilibrium we saw. So, x equal to 0 is always an equilibrium, but when mu is positive it is kind of stable, whereas when mu is negative it becomes unstable. Now, when mu is minus 1 by 4, something funny happens. Out of the blue we get 2 new fixed points. But we see when mu is positive, only these two survive, these two they disappear, right. So, they kind of merge, and then they disappear. There are only 2 fixed points. So, when mu is positive, 2 plus 1, 3 fixed points including the origin, and in this range when mu is bigger than minus 1 by 4 and negative, we have 5 fixed points, and here as usual we have only 1 fixed point. So, if you look at the reverse, what is happening? If you look at the reverse, as mu changes from positive to negative, there is an unstable equilibrium that is becoming stable and giving rise to 2 other unstable equilibriums. So, these must be unstable strictly speaking. So, so one of them is stable, the other one is unstable. So, unstable equilibrium is becoming stable and giving rise to 2 other unstable equilibrium. So, this is nothing but a pitchfork bifurcation. So, what is happening here when mu equal to 0? So, when mu equal to 0, we witness a pitchfork. So, that means if you locally zoom this diagram, if you zoom this and look, it will be a pitchfork bifurcation. Now, when mu is minus 1 by 4, we have 2 saddle node bifurcations happening simultaneously. So, these are 2 saddle node bifurcations. If you put the mathematical conditions and check at x mu, you will indeed find that these are two simultaneous saddle node bifurcations. So, this is the bifurcation behavior of the dynamical system. So, if we add x power 5, if we did not add x power 5, then we add only this part of the diagram. So, this zoomed part. So, this happened when you do not have x power 5 ordinary pitchfork. Addition of x power 5 in the dynamical term gives rise to these other behavior, these other branches. So, we now have 5 branches now. So, with this we complete this problem. So, we will now move on to the next problem. Now, here I present to you a dynamical system in 2 dimensions R2, but you see that it is not a really 2 dimensional example, because one of the variables, the dynamics, is very independent and trivial. So, I use polar coordinates now in R2. To recapitulate, polar coordinates in R2, a point is characterized by r and theta, where r is the distance from the origin, which is always positive, and then theta is this angle. So, we will take r to be positive and theta to be belonging to minus pi to pi. So, this dynamical system that I give you here is kind of a dynamical system in polar coordinates, but in the polar coordinates we have a very simple behavior where we have r dot is equal to r into mu minus r square, whereas theta dot is equal to minus 1. So, we see this dynamics of theta is independent of r, and it is quite simple. It just keeps on increasing at a constant, decreasing at a constant rate of minus 1. So, this clearly means that since theta is this angle, this essentially means that the point here moves clockwise, because theta is anti-clockwise. So, theta dot is minus 1 implies the point moved clockwise at a constant angular velocity of 1 radian per second, because theta is an angle. So, the derivative d theta by dt will be the angular velocity, right. So, this just says that wherever the point in R2 is, as far as the theta behavior is concerned, it will keep on moving around the circle in minus 1. If you look at the projection of this dynamics on circle, it will just move at a constant speed of 1 clockwise. That is what this equation is saying. It is the dynamics in the R that is of real importance to us. So, what is happening? Let us see. So, the dynamics is r dot is r into mu minus r square. So, when r dot is equal to 0, what happens? So, let r star be let r dot equal to 0 at some radius, let us say r star. What does this really tell about? So, when let us say r star is positive and we have dr by dt at r star is equal to 0. So, this just says that the radial vector joining the point to the origin, this remains fixed. So, r remains fixed. So, this really says that the particle remains on the circle. So, if the particle starts on the circle of radius r star, it will remain at r star, okay, and hence, but theta dot is minus 1. So, it has to keep moving clockwise. So, when we have a non-zero r star that is becoming 0, what will happen is the particle, when it starts anywhere on this circle, it will just keep on moving with a constant angular speed of 1 clockwise. So, this corresponds to a periodic orbit when r star is positive. Again, this r star has to be positive. Now, when r star is 0, what happens is r equal to 0 is not a circle, it is essentially a point, right. So, when r star is equal to 0, so at r star equal to 0, if dr by dt of r star is equal to 0, then the circle collapses or degenerates to a point. So it's essentially an equilibrium. It's not a periodic orbit, only an equilibrium, because the particle, it starts here, it stays here, it stays at r equal to 0, which means it's essentially an equilibrium, right. So this is the thing that we need to be cautioned about. So the equilibrium points of dr by dt dynamics, if they are positive, then they are closed orbits, but if it is 0, then they are it's an equilibrium point. When r star is negative, doesn't make sense, they are not acceptable values, because the distance from the origin is always positive. So we have to discard any negative solutions we get for this equation. So let's analyze this equation. Dr by dt is equal to r into mu minus r square. So one solution is r equal to 0. So this becomes 0 if either r star is 0, which means it's an equilibrium at origin, or r square equal to mu. So this again of a quadratic equation. Two cases, when mu is negative, there are no solutions, so which implies there are no closed orbits. When mu is positive, we have r square is mu, which implies r is plus root mu, r minus root mu. But as I said, negative values of radius doesn't make sense, r cannot be negative, so we can have only positive values of r. So this corresponds to a closed orbit when mu is positive at radius root mu. Now what we have to do is we have to analyze the stability of the equilibria and the limit cycle. So go to the last page. Dr by dt is equal to r into mu minus r square, which is nothing but mu r minus r square. So when r is small, we have dr by dt is approximately mu r, because we are neglecting this when r is small. So when mu is positive, we see it is unstable, because it has a solution r of t grows as e power mu t, so it is unstable, it grows. Whereas when mu is negative, this is stable. But when mu is positive, so the origin is unstable. When mu is negative, origin is stable. But when mu is positive, we have a closed orbit, right. So we have a closed orbit at plus root mu. So there exists one closed orbit, and when a mu is negative, there exists no other closed orbit. And if you look at the linearization about r equal to root mu, if you plot this function mu r minus r square, so let this be r and let this be f of r, which is mu r minus r square. R is positive, that is the value we are bothered about. When initially when mu is positive and very small r, it will look like mu r graph, and then the minus r square term will take over. So if you see, there are two equilibrium. Between here to here, this r dot is positive, so the radius always increases. When r is bigger than root mu, it decreases, because this is negative. Dr by dt is negative here, dr by dt is positive here. So we see this closed orbit is actually stable. So what is happening here is, when mu is positive, when mu is negative, there is only one stable equilibrium point. So origin is stable equilibrium, and any trajectory kind of settles to the origin. Whereas when mu is negative, origin becomes an unstable, and we can calculate it becomes a focus indeed, because theta dot is minus 1, so it has to keep rotating clockwise. So if it keeps rotating clockwise, it spirals out, but there is another closed orbit at r equal to plus root mu, and this is stable. Any trajectory starting above it will come below and settle, anything starting below will come above and settle. So when mu versus R. So, initially we have only a stable origin. So, this is stable origin, and after mu becomes positive, the stable origin becomes unstable and gives rise to a limit cycle or a closed orbit at r equal to mu. So, this is r equal to root mu, because a square root function will look like this, right. So, this is when mu equal to, after mu is positive, it becomes, so we have a stable limit cycle. So, this is nothing but the signature of a Hopf bifurcation in 2-dimensional systems. So, we analyzed this Hopf bifurcation, even though it is a 2D bifurcation, we analyzed it in 1D because we could make use of polar coordinates. Why we could make use of polar coordinates? Because all the limit cycles are circles here. So, with this we complete the recording. So, thank you. So, if you have any clarification, you can ask in the forum for further details.